Hey guys, just want to give you a brief introduction on carbon NMR, and I want to tell you all the things that it can do. Carbon NMR is similar to proton NMR, but also unique and different, and I'll tell you why. The first thing is that with carbon NMR, you need to create a much more concentrated sample and or have a more sensitive receiver coil. And this is because the carbon-13 isotope that we're looking at in NMR accounts for only about 1% of the carbon atoms in nature. Whereas in proton NMR, the isotope that we're looking at is the one that is the most abundant, which is just hydrogen. In carbon NMR, only look at the number of signals and the chemical shift. We don't have to worry about splitting because often the splitting is so complex that it's unreadable. And so what we'll do is we'll acquire the spectrum in a decoupled manner so that we're really only looking at singlets for carbon NMR. And the other big difference is that in the x-axis, when we compare our signals to TMS, we're going to be looking at an x-axis value of 0 to 220 rather than 0 to 12. So just like in proton NMR, in carbon NMR, if your molecule has symmetry, then it will affect the number of signals that we see in the spectrum. So the molecule all the way to the left here has 4 distinct carbons that are in their own special unique environment. And so that gives us 4 signals. In the center, because we have the line of symmetry right down the center of the molecule vertically, we end up having 5 unique environments and therefore 5 signals. And the molecule all the way to the right, we see a plane of symmetry both in the x and the y axes, and so we end up only seeing 3 signals. The next thing we'll talk about is chemical shift. And so if we look at our x-axis from 0 to 200, here's typically where you'll see things appearing. C double bond O is going to happen in between 150 and 200, so that's the carbonyls. C double bond C happens in between 100 and 150, both for just alkenes and for benzene. From 50 to 100, we're going to see C triple bond C and C single bond O. Also, we see carbon bonded to nitrogen, chlorine, and bromine here, and this is going to be sp3 hybridized carbons that fall down in between 0 and 50. And again, you'll be given a table for these values as well. So if we talk for a second about the idea of decoupling our signals in carbon NMR, here's a schematic that shows the difference. And so for proton decoupled, which is very typically what we're going to run for carbon NMR of 2-butanol, shown here, we see this nice signal where we have 4 distinct carbons, and you can see that the closer you get to the OH, the further downfield you're shifted, just like in the proton NMR. But for each signal, we just see 1 peak. For each different type of carbon, we see a singlet. And that's how we're going to very typically look at carbon NMR. If we did look for a second at the coupled version, it's much more complicated. And typically that's not necessary. We can get whatever information we need from the decoupled. The other thing is the intensity of the signals in carbon NMR. So we don't have to do the area under the curve. We don't have to integrate. And so if we look here, we see TMS at 0, and then we see 4 peaks. This one, here, here, and here. And so if you see the molecule we're looking at, we have these 3 methyl groups. So these 3 carbons are the same. And so they're equivalent, and so they're going to give 1 signal, and that is going to be the very tall signal. So you can see here that the intensity of the signal is related to the number of carbons that are in that signal. So this methyl group here should be about 1/3 of these 3 methyl groups. And so that is about here. And the last thing I want to tell you is that carbons that do not have any hydrogens attached, these quaternary carbons here, give a very small signal. And so that's the one that you see here. So let me tell you a little bit about a special type of experiment that we can do to learn about the hydrogens that are connected to carbons in carbon NMR. And this experiment is called DEPT. It stands for Distortionless Enhancement by Polarization Transfer. And it gives us information about the hydrogens that are attached to each carbon. So it's going to be a series of 3 reactions, 1 normal carbon NMR spectrum, a DEPT 90, and a DEPT 135. And then we'll compare the results from those 3 experiments, and we can figure out how many protons are on each carbon. And here's how that happens. The DEPT90 only gives signals for CH, so only tertiary carbons give a signal in DEPT90. DEPT135, however, gives signals for primary and tertiary, and then it gives negative signals. In other words, the signal goes below zero for secondary carbons. So if we compare the broadband decoupled spectrum shown here at the top, we see all carbons. Then we compare that to a DEPT90 and we see only the tertiary. And then if we compare that with the DEPT 135, where primary gives a positive signal, tertiary gives a positive signal, and secondary gives a negative signal. And then again, the quaternary carbons don't show up in either of these two special experiments. So this series of experiments allows us to determine primary, secondary, tertiary, and quaternary carbon, which is very helpful. And so here's just a quick example using this molecule right here. And so you see at the bottom is the decoupled, all carbons show up here. And here, this would be the DEPT90 where we only see our tertiary showing up. And here we see the secondary showing up. So these ones would be the ones that turn up negative in our DEPT 135. And then here's our CH3 or our primary carbons that would show up positive in the DEPT 135 and not show up at all in the DEPT 90. So this is a very useful technique to look at protons, even though we're really looking at carbons. And next, I'd like to tell you about another special NMR experiment, which is called COSY NMR. COSY stands for correlation spectroscopy, and it gives us a two-dimensional look at proton NMR. And so we have proton NMR spectrum shown here, and it's correlated to a spectrum here. And so the COSY spectrum identifies proteins that are coupled. And by coupled, it means that it's on the carbon next to it or related somehow through bonds. And so if we look at the cross peaks of this two-dimensional display of proton NMR, the things that match up on the diagonal line are coupled. And so this gives us more information about the three-dimensional structure in terms of the protons. So technically, this isn't part of carbon NMR, but it is an advanced technique within NMR. Lastly, I want to talk about MRI, magnetic resonance imaging. You've probably heard of it. You may have even had one done, right? So this is a technique that doctors use to get insight into the structural features inside the body. MRI instruments are essentially proton NMR spectrometers, and a body is being analyzed rather than a sample in an NMR tube. It turns out that our different tissues have different concentrations of protons, and so we can clearly see it that way. The MRI gives a three-dimensional image of our different tissues, but for MRI, the radio waves and magnetic fields are very mild, so there's no side effects. There you have it, carbon NMR. It doesn't give us quite as much information as proton NMR, but it's definitely going to be helpful when we're trying to solve the structures of our compounds.